Okay, so now we are progressing to the next formalism of the object-oriented perspective, and that is going to be the depth formalism. So before we go into the depth formalism, let's look back the case of the Petri net. Here we have a Petri net model, and do you remember what kind of what this model represents? Yeah, this was what? This was like eating, and this is eating, right? Eating transition and thinking transition, and these are the fork, right? Fork and eating or thinking places, right? This was the philosopher case, right? So we were able to model 5 entities. 1, 2, 3, 4, 5 philosophers and 1, 2, 3, 4, 5 forks to each spaghetti. And this Petri net model, even though this represents such kind of interactions between the philosophers and the forks and the next philosophers, however, the entities here do not have boundaries. Here, this area is a kind of a philosopher model, one single entity, one single human being. However, there is no boundary here, right? There is no boundary, meaning that it is not easy to scale this 5 philosopher model to 10 or 100 or million philosopher models, meaning that we need to have a certain boundary of a certain entity so that we can interact with each other as a block model so that we can be scalable. However, this Petri net formalism does not support that particular scalability coming from the abstraction by making this as a one entity block model. Okay. Moreover, so complex entities are very difficult to model, and also furthermore, designing states are very difficult. Do you remember that each of these places are not states? Yes. The token assignments over these places will create a one state over the systems across the entities, across the 1, 2, 3, 4, 5 philosophers. So that designing the state of this system as being a one whole system, not for a single entity or some of this single entity. Because of that, designing states are difficult. If we were able to say that, okay, this philosopher has a certain state and this philosopher has a certain state and so forth, then we may be able to make a state for each of these philosophers, and we may be able to say that some of these states will become the system state. However, here it is not such a case because we do not have an entity boundary here, right? So Petri net has difficulties in creating a single object. Also, as an abstract model, we explore the finite state machine and its formalism, okay, and its notations. So the problem of finite state machine is this. So this is one clear example of a finite state machine which has how many states? 1, 2, 2 states. Opened and closed, and we have state transition like this, okay, coming in to the closed state and going out and coming in to the opened state. What's the problem of this finite state machine? First, it is very difficult to expand to a larger model. Why is that? Because we still have to make this being expanded without utilizing hierarchy, okay? Without utilizing block model, without utilizing abstractions. So that we have to include all these states and interactions, right? So it will become a much more complex issue to make a larger system, okay? Already being discussed. However, I want to focus on more fundamental problem here. this is a difficulty, not infeasible. Okay, this is still feasible. If we spend time and money and our effort, we can create a large machine out of this finite state machine specification, which we already do in some digital systems. However, there is no feasibility. It's completely infeasible to perform self-transition of this finite state machine. Let's assume this. Okay, this is a door. Door being opened, door being closed. There is an event to make the transition. Okay, so one transition is closed door transition. Another transition is open door transition. Okay, good. Door, it can open, close, perfect. However, let's imagine this as being what? Automatic door. Let's imagine that. Let's imagine this is being automatic door and door is being closed like this and door being opened like this and then turning back. Going back and forth, going back and forth, right? And having said that, here, if someone gets nearer, there is this open door transition transition event. However, will it keep being opened until he leaves? Until that someone triggered this event leaves? Then will this door still being opened? Nah, it should be closed, right? Meaning that after some time, this automatic door needs to be closed and it has to make a self-transition, self-initiated transition without any outcoming event, right? So let's assume this door is being opened and door is waiting for the closing signal, but there is no one to send the closed signal here because someone already left, right? There is really no entity to send closed signal, meaning that it will require what? Self-initiations, okay? So finite state machine does not have an internal state transition. Okay, there are two different transitions. One is external state transitions. Okay, and the other transition is internal state transitions. Okay, external state transition is being triggered by outside event. Because of that, it is saying it is being external. However, internal state transition is being caused not by outside event, but by internal what? Imagine that. What? To make this work? Internal timer. Okay. There is an internal timer. Once the timer is expired, alarm goes off, then it will create a self-initiating internal state transition. Like this. After some time, the automatic door will be closed by itself. So it is being named automatic door. Right? Right. So if we specify the system like this state machine, then self-initiation, there is no timer specification here. So that this such specification will make machine only to react to the outside stimuli, outside event. And particularly, this is not an ideal or realistic modeling practice when it comes to human being. When it comes to human being, human has their own self-initiation, self-motivations, right? to initiate behavior by themselves. So that we definitely requires one such kind of differentiations of state transition. Here, state transition was just a single. All the state transition here was outside event triggered, so that all of these are external state transition. However, now we are saying there should be internal state transitions. Okay, so then machines that can react upon the outside event as well as to what? Internal event, internal timer being going up. So internal event and external event, all of these two approaches should be feasible. Without that, it is very difficult to utilize finite state machine in modeling human being. Now let's look back the formalism of the cellular automata, whether it has such kind of transition idea or not. So here, cellular automata formalism is specified as this CA, okay? And here, CA represents what? Gamma as graph structure, okay? Connections of these cells, right? And this defines the space, okay? And Q is a set of states that a single cell can have, right? So we have one black, pink, cyan, and these three states. And N is a definition of the neighborhood, von Neumann neighborhood, Moore neighborhood. Neighborhood are being defined, and delta is being what? Delta is the local dynamics, rule of change, how to change the cell of the center by being influenced by the neighbor and by self. Okay? So here, delta is what? Delta is actually the transition. Here, it specifies what? It specifies the neighbor, and by self, it will make a new self state. Okay? So this is the transition and behavior rule of these cellular automatas, one cell, a single cell. And finally, X is a configuration of mapping from graph to the state sets. Okay? So how to map each of these nodes to a certain state, and that is being X. And having said that, so transition, this delta, what kind of this delta is in terms of from the perspective of the state transition? First possibility is the internal state transition, and second possibility is the external state transition. And this is what? This is clearly, yes, external state transition. Why? Because the outside cells provides, now it is being said like this, being said like this, being said like this. Outside information is being utilized to change inside state, right? So the external setting influences to set the state of the center cell. So that this is an external state transition. There is no internal state transition because there is no timeout here. There is no timer here. So that internal state transition is not being defined in the cellular automata. So that, what can we say? So that we can say that cellular automata is insufficient to model a certain human being's self-initiated behavior.